last but not least, we have Waterfall. And I am Malika, again, to introduce myself for those of you who have joined. I'm one of the design interns and ended up doing a little bit of development on this project. And I'm a master's student in computational design at Carnegie Mellon.
And I'm Noah, the other designer on this project, and also contributed to the development a little bit. And I'm a master's student in design engineering at Harvard.
And we also had Maalvika Bhat contributing to some of the CS development, and she is an undergrad student at Olin. And we were really happy to work with JT and Kyra, both of whom are working at JPL and have been awesome collaborators, and they're doing really impactful work that you'll hear about in a second. So Waterfall is a tool to visualize the Drought Cascade in California. And again, here's a little sneak peek of the design of the tool. But to go into the bigger context of it, I think most of us are probably aware that California is facing a water crisis. And it's also in the unique position of being sort of the agricultural hub of a lot of the United States, providing a lot of produce for the whole country. And so this provides a really challenging situation. So when there are times of drought, farmers in California have to draw on this hidden and essentially non-renewable underground source of water called groundwater. And the way that they do that is by pumping it. But pumping of groundwater has historically gone pretty much unchecked. And we're starting to realize a problem because groundwater is kind of the buffer or the cushion for the whole water system. And as we keep depleting that puts an even bigger risk during times of drought. So policymakers are starting to find that they need to place limitations on pumping to mitigate even bigger crises in the future. And in order to do that, they need an accessible way to understand all the relationships between the different parts of the water system. So water inputs, this pumping activity that's happening, and the actual groundwater levels. Of course, it's not that simple, and there's a lot of challenges with information access that have made it difficult to understand those relationships, and they've led to more reactive rather than proactive management of water. So the first problem is that data that's been collected on water levels is pretty sparse in space and time. So you can see on the right is well data that was collected over California. And in certain areas, it's a lot denser, but those observations that they're taking are not really regular over time. Thankfully, JPL is playing a really big part in addressing this problem through its GRACE satellites, which have given researchers the ability to actually remotely monitor groundwater levels from space. So Kyra and JT, the researchers we've been working with, are using GRACE data along with other data to actually use it and build these models to address the second problem, which is that this pumping activity that's happening is essentially a black box because it's not tracked at all. There's no way to know how much water is being pumped unless we look at sort of the state after pumping happens. So they're building models based on this GRACE data to actually shed light on that black box and give policymakers a better picture of water use in California. And finally, the other problems are that the data for these different hydrological layers involved in the water system come from so many different sources and in totally different file formats. And existing tools that try to bring this together are really difficult to navigate, and they don't really support analysis between the layers. So there isn't really a clear and accessible way to actually bring all this together and understand the relationships between groundwater levels and these other water layers, as well as pumping. So the task that we set for ourselves is essentially to bring all of these data layers of water together and provide a straightforward but comprehensive view of these layers so that we can start to understand the cascading relationship between them, the kind of cause and effect between, you'll see on the right, precipitation, snowpack, surface water or reservoirs, and groundwater, which is as that water seeps into the soil, it starts to replenish that underground store. And specifically, we wanted to support understanding when, where, and by how much water inputs, like you see on the right, will impact future groundwater levels. And as Noah explained before, our process is kind of similar for all the projects. So we started with contextual inquiry, which involved a lot of time spent with Kyra and JT, understanding their work with modeling and kind of the bigger context of the work that they do and how they're really narrowly focused on modeling groundwater, but having this bigger context of the other hydrology layers gives them a ton of value. And after that, it was followed by all these iterations of design and data exploration and making sure we understood the problem correctly, all of which led to today's prototype, which Noah will go into. Oh, sorry. Actually, first I will talk a little bit more about our process. So yeah, these were a lot of the explorations we tried along the way. And I think some of the main things that we found were that there's a lot of value to seeing these different hydrology layers changing alongside each other, both in time and space, and especially exploring this idea of multiple stacked time series to see seasonal cycles and this cascading effect alongside different map views to see the spatial effects.
And our solution is Waterfall, which centralizes all these different layers of hydrology data and really allows our users to understand these changes across the sort of 3 dimensions that we care about here, which is time, magnitude, and space, all of sort of which supports the building of intuition about these relationships that will hopefully inform future planning. Just to give a quick overview of the tool before we jump into the demo, we have basin selection. We can switch between these different view modes that we'll talk about. We can select a different time range. And that brings us to sort of our main view where we have a 3-year time series view that's taking up the majority of the screen. We've got this, what we're dubbing a flower plot, which is allowing us to see sort of all these attributes and their values together. And then there's a map view that's able, you can kind of drill in a little bit deeper and understand the spatial relationships. Now we'll switch over to a demo. And I'm going to ask you all to imagine that I'm a hydrology researcher at JPL for the sake of this demo. And I also am going to ask you to imagine that we're traveling back in time to April 2020, which is the latest year we have data on, although the future of this tool will be incorporating real-time data. So we can imagine that it's April. Here we see our 4 attributes, precipitation, snowpack, surface water, and groundwater. And we see a time series chart for each. And what you're seeing here is the black bars are representing the mean for each attribute for each month for all the available data that we have. And I can see here in my waterfall tool that the snowpack this year is lower than normal. It's actually falling below the mean. And as a researcher, what I want to do is get a sense of how this low snowpack might impact California groundwater levels in terms of those 3 dimensions, time, magnitude, and space. And really try to understand how worried should I be about this low snowpack. So I'd like to find a similar year, maybe, where we had low snowpack and use it as a precedent and try to see how that low snowpack might have impacted these other layers. I can tell from my time slider that we've got some low water years somewhere in the 2011 to 2016 range. And so I'm going to drag the time slider to 2011 and take a look. As you can see, for all these years, we have these really nice seasonal cycles that are emerging. And we can scrub over these time series charts and see in the top right corner the value of each layer relative to each other and also relative to their mean, which is in black as well. So we can kind of see how these things are fluctuating. And we can also see how these values vary spatially on the map below. And here you're seeing that for groundwater in particular. I can see that in 2012, we had a low snow year, but it didn't really look like it impacted groundwater levels that much. So maybe what I'll do at this point is take a look at 2012 to 2014 and see how this plays out. So this is actually getting pretty interesting. It looks like in 2013 and 2014, we had more low snow years. And here we really start to see it dramatically impacting both groundwater and water levels. At this point, what I'm going to do is switch to my snap to mean view, which is going to show all the values relative to their normal sort of monthly mean. And this is providing me with a really clear way to see just how much a few years of low snowpack can really start to impact groundwater and surface water levels. Even as rain kind of stays relatively constant. We had a little bit of a low year in 2013, but not as much of a fluctuation as we're seeing with the other ones. So just the snowpack changing is actually having these dramatic changes in reservoir and groundwater data. And I might want to take it a little bit further and look at how the slow groundwater is varying spatially. And here I can sort of look at the map and scrub across the timeline. What I'm seeing is that while groundwater sort of does get low during these times of drought, there is this cycle of replenishment, and sort of as we scrub throughout a year, you'll see the map getting lighter and darker. But there's this kind of gray sliver in the middle of the map where we don't really see that happen. It's just kind of low all the time as we scrub across the time series. And what's really interesting about that is that's actually where the Central Valley is in California. And that's telling me that that's an area that I really need to pay close attention to. We're not seeing the same sort of cycle of replenishment in this area. And what's so exciting about this tool is that I was able to sort of very quickly get some key takeaways about what this year's low snowpack might mean for future groundwater levels by looking at these historical precedents. You know, I've been able to learn that it really takes multiple years for low snowpack to have a big impact on groundwater levels. So while I might be worried, I know that I should be really worried if next year we see low snowpack as well. And I've also learned that we need to be particularly concerned about the Central Valley in terms of groundwater. And at this point, I might kind of go drill in further and try to understand where in the Central Valley in particular these levels are low. But now I'm able to share this data in this tool with my partners at the Department of Water Resources and really inform how they're going to decide to regulate pumping in the coming year.
Awesome. And now we can talk about how we actually built this. So one of the big challenges with this project was actually getting the different data layers together. As we mentioned, that's kind of been one of the main things that's also kept it from being useful to policymakers and researchers, is just bringing all of that together. So that was a big part of the development, was just getting the data from different places and also converting GRACE geotiff images to CSVs, all of which we did in Python, and then processing all that data to a single format, just so that we could treat all of it the same way. And that, again, was also in Python. And some of what we did was binning all the data monthly, because some of it was daily, which was just way too big of a file to deal with. And then also binning it by California basin and gridding it to a 1/4 degree, which is the same resolution as GRACE, the groundwater data. And also computing that difference from average per month and per basin. So that was when you saw the bars above and below the baseline. And also smoothing the data using a rolling mean with a 3-month window, because especially with the rain data layer, that oscillates so much that it's actually more useful just to smooth it out to see where, say, if you have like 3 months in a row of a lot of rain, that actually starts to mean something rather than just 1 month of a lot of rain. And finally, we developed this interactive prototype that you saw that actually allows users to visually explore the data once it's in this single format. And that we did using P5.js. So it's a JavaScript-based framework. In terms of future work, we see a lot of opportunities to keep adding more functionality to this. So right now it's a fixed 3-year window that you're looking at. And that's because you can focus on a single year, as well as kind of the like peripheral vision around it. But we could imagine users wanting to select bigger ranges than that. Also changing different bin sizes for the map. So changing that size of the grid of the map. And then smoothing all the layers more. And I think there's a lot more sort of data analysis that could happen. Another big piece would be just building in more data layers. So right now we're just looking at precipitation, snow, reservoir levels, and groundwater. But as I was mentioning, the whole water system is really complicated. There's a lot of different pieces involved. And so things like building in things like soil moisture, or even the geologic texture, and subsidence, which is when the land sinks in reaction to groundwater being pumped out. Bringing all of that in would just augment the value that this tool gives and broaden the perspective that it offers. And finally, as Noah mentioned, actually incorporating real-time data would be really valuable, so that there's this immediate pipeline for pulling in real-time data, processing it the way that we did, and seeing it visually in the tool, so that you can start to diagnose what is the year ahead going to look like based on the rain and the snow that I'm seeing right now. And also, as you saw Noah doing sort of intuitively, we could start to build in things to the tool to support finding those historical precedents where you're looking at this year, there's much lower snow than average. Let me find other years where that was the case and see how that played out. And we could start to do that computationally. And again, to summarize our contributions here, before there were kind of these different layers of data in different formats. So there's a geotip image from Grace, and then some basically CSVs coming from for the other data layers, all from different places. And after we have this tool to really easily and intuitively see the time relationships between these different layers all in one place, alongside getting that spatial view of it too. And we see a lot of ways that this could, as we were talking about, that this could continue to be more useful as we build in even more functionality. And we're just really excited that we can contribute to such a pressing problem, especially in California. And again, we want to thank our awesome partners, JT and Kyra, for the time that they've spent with us, helping us understand this problem space and the work that they do, and just giving us the opportunity to do this. And thank you again to our mentors, Hillary, Santiago, Maggie, and Scott, for their help throughout this process, and their support in helping us understand the problem and get to this awesome final design. So again, we can open up to questions.